Hi everyone, in this video I'm going to go over the sampling distribution of estimators for least squared regression. And before we get into it, I want to make sure that we're all on the same page with what assumptions I'm using and what the dimensions are of the different things I'm using. And I'm using pretty typical notation, but some notation does change from book to book. So in this case, I'm going to be working with beta hat, which is typically a p by 1 vector, and I'm going to define it as x transpose x inverse times x transpose y, where x transpose is equal to p by n dimensions, x is an n by p matrix. Again, we have p by n and n by 1. So as you can see, the dimensions of this side is equal to the other side. And I think it's really helpful to always check your dimensions, or at least check them periodically, and make sure that what you're doing is equaling and you're on the same page, so to speak. The other assumptions that I have is that y given x is distributed normally with mean x beta plus epsilon, where beta is a vector, epsilon is a vector, and it has variance sigma squared times the identity matrix, which is an n by n matrix. We also have the error terms, which is a vector. The error terms are also normally distributed with mean 0 and variance sigma squared times the identity matrix. Note that I actually didn't need to write epsilon right here because it is equal to 0, or the mean of it is equal to 0, which we see here. Now, when we try to find the sampling distribution of beta hat, what we're really asking for is what is the mean and variance of beta hat. That's typically what we're getting after. So first we're going to check, we are going to find the expected value of beta hat. So let's scroll down. So by definition, we have that we can substitute x transpose x inverse x transpose y. And this is by definition of beta hat. We know that the x's are observable random variables. So in this case, they are actually constant. So we can pull the x's out. X transpose x inverse x transpose times the expected value of y, because x's are observable and constant. So although they are random variables, in this case they are constant. Next, we can substitute the y value because we have assumptions about y. So x beta plus epsilon. In this case, beta does not have a hat because we assume that it has a specific population parameter. This is by assumptions of y. Again, we know that because expected value has like these linear properties where we can break up the expected value linearly, and we know the expected value of epsilon is 0, this actually just becomes 0. So we only have to worry about this side. We can pull out the x again for the same reason as before, because x's are observable, and in this case they are constant. So I am going to just copy this guy. Whoa. Third time is, all right. X is constant. That's why we did that. By linear algebra rules, this guy is actually just equal to an identity matrix. And an identity matrix times another matrix or vector is itself. So this just becomes beta at the end of the day, which leads us to conclude that the expected value of beta hat is simply equal to beta. This is by linear algebra rules. So we've got step 1 of the problem. Now we are working on finding the variance of beta hat. So find variance of beta hat. Again, we can kind of do the similar steps where we can substitute beta by what it's defined to be, by beta hat definition. By variance properties, we know, again, the x's are observable and hence constant, and when we have the product of a constant term times a random variable, we take that constant term out and we square it. But since this is linear algebra and we have matrices, we actually have to follow some linear algebra rules. So we'll take our matrices out. We have the variance of y, and we transpose the other side, which rearranges terms a little bit. This is a transpose, this is transpose. Now this is not a linear algebra video, so if you're getting a little lost in what I'm doing, you should look up linear algebra rules, specifically regarding transposes and inverses, and variance rules. So next we can substitute y via our y assumption, so x transpose x, inverse x, and we know the variance of y by assumption is just sigma squared times that identity matrix. We can move, this is by y assumption. I also could have plugged in x beta plus epsilon, because x beta is not a random variable. The x's are observable random variables, and the beta is a unknown parameter, which is not a random variable, and then I could have taken the variance of epsilon instead. This is a little faster, but that way would have also worked. We can move sigma squared because it's just a constant, and it is fine to move constants when multiplying matrices. We also have this identity matrix, but an identity matrix times another matrix with similar properties. Again, this is n by n, this is n by p. We end up just getting the same matrix, x transpose x inverse, and this is linear algebra rules. This becomes an identity matrix itself. Again, identity matrix times another matrix is just the second matrix. So we have sigma squared x transpose x inverse. We can't simplify it anymore. So we have that the variance of beta hat is equal to sigma squared x transpose x inverse. Now this basically gets us what we want to know. We now have the distribution of beta hat. So expected value of beta hat, sorry, these should have all had little vectors on them, or little bars under them, is equal to beta, and the variance of beta hat bar is equal to sigma squared x transpose x inverse. And that's it.